it's okay sometimes to not have emotions about things. You can have lots of emotions about things, but you can also be like, I don't need to have an emotion about that because it's not that important. So that's also fine. All right, so here we are on page 15. If your pages aren't numbered, then we're somewhere in the middle of 11.1c and you're looking for the little table. So please try and find that. And if you are unable to find it, let me know. Huh? We'll see. Are we there? Shh, are we there? We're there? On page 15. Have we all found it? Everyone has found it? Yes. Okay. So sigma, if you recall what we were talking about yesterday, is caused by head-on overlap, which could be an s orbital with an s orbital, but it could also be a p orbital overlapping with a p orbital as long as the overlap is head-on. It could also be an s with a p as long as we have that head-on arrangement. Whereas with the pi, we have the sideways overlap. So if you remember, our p orbitals have three orientations: up and down, side to side, and front to back. Yes? So when they are side to side, we get head on. What kind of bond is that? Sigma. When we have up and down, what kind of bonding is that? Pi. And when we have forward and back, what kind of bonding is that? Pi. Okay. Sigma, pi, pi. Yes. All right. I feel like at your grad, I should like have somebody write like a Sigma Pi Pi song and we could play it. Yes. No, that can't happen because that would be where the node is. So there's no density there for it to overlap with. Right? So he was like, can this happen? No. Okay. Now, sigma bonds, where is their density? Along the internuclear axis. Where are pi bonds? They are either above and below or in front or in back. They are on opposite sides of the internuclear axis. They are not on the internuclear axis. So they are around the internuclear axis in essence. Sigma bonds are present in single bonds, double bonds, and triple bonds. You cannot have a double bond without having a sigma bond. It's the one you start with. But pi bonds, you can't have like a single pi, like a single bond with that's a pi bond. It just is not a thing. It will be present only in double bonds. It is the second and third bond in those double and triple bonds. Now, end groups can freely rotate. I forgot to bring my molecular models today. Oh, phooey. But this is a little picture. I'll bring them hopefully tomorrow. I know, just stop talking about it so we can get through this and then maybe we'll have time to do it. Yes? Okay. End groups can rotate freely. So if you look at this little guy here, this is chloroethane. This is CH2 with a Cl attached to it, yes? So we have the C and the H and the H, and here we have a Cl. So CH2Cl and then CH3. Now what can happen is that this, just like on a, this can rotate so that this stays in position. This one over here stays where it was. And now the Cl, instead of being at the bottom, is at the top. So it can rotate. All right. But what if instead of having a single thing like this, where you can rotate. Yes, I can go like this with my fingers, right? What if I had like this? Can I rotate my fingers now? No, because if I try and rotate my fingers, what happens? It's going to break. Yes? So you can even do it just yourself. You can be like, I can rotate my fingers around a single point, but I cannot rotate it around 2 points. So that's why single bonds can rotate and double bonds can't. Okay? And what that leads to is the fact that this is the same molecule as that. There's nothing different, just one end of it has spun. But if we have this one, this has the two chlorines locked in position on the same side of the molecule. Okay? The Cls are locked in position on the same side of the molecule. On the other hand, you could have the chlorines attached so that one chlorine is on one side and this chlorine is on the other side. And that is a different molecule and it will have different characteristics. Like it will have different chemical properties. It won't behave the same way. Okay. Have we talked about the term isomer before? Maybe not very much. Isomer. Isomer. You might have had it in the summer, yeah. Because I think they might have talked about it with alcohols, yeah. So an isomer, we have the same molecular formula, but we have, if we have two different isomers, we have different structural formulas. So iso means the same, okay, iso, the same just like isotope, different versions of the same element, okay? And if it has a different structural formula, it will have different chemical properties. Different chemical and physical properties. So let's just say different properties. Can I scroll back down? So what do we have here? We have a molecule that is made of 2 carbons, 2 hydrogens, and 2 chlorines. So the molecular formula for this would be C2H2Cl2. Yes? Our other isomer has 2 carbons, 2 hydrogens, and 2 chlorines. So its structural formula will be C2H2Cl2. These are the same, but these two are different. This is our structural formula, and those are different. That's what makes them isomers. So, prefix trans, it means across. So if you go on a transatlantic journey, what are you doing? You are going across the Atlantic Ocean. Yes? If you go on the Trans-Canada Highway, you are traveling across Canada. Okay? And you can see that the two chloride ions are across the structure from each other. Okay? So when you have the atom of interest is on opposite sides, you have to go across the molecule. That is called the trans isomer. Cis, I'm not sure that it means the same, but that's how I think of it. Okay, cis is like on the same side. And in fact, have you heard of, and I'm sure you have, cis and transgender? Now, where did they come up with those terms? Somebody went across Canada. No, somebody had done organic chemistry and applied those terms to genders. I'm serious, this came first. Okay, so if you are cisgendered, that means your gender is the same, like whatever your biological gender is the same as what your gender in your head is. Yes? So it matches. But if you are transgender, it means what's going on in your head and what's going on in the physical body are on opposite sides. Yeah? So that's where cis and trans originally came from. So it was so funny when they were doing, like, you know, several years ago, they had education for us at our Pro D Day, and they were talking about cisgender and transgender because these were more new terms back then. And all of us chemists were like, oh, no, you don't need to teach us. We know what that means. This one's the same and this one's different. And we're like, yes, we understand because we're organic chemists. Anyway, that. Oh, of course we did, but you know, it's okay. All right. Anywho, so that might help you remember that cis means they're on the same side and trans means they're across from each other on opposite sides. Okay. There are lots of different kinds of isomers. If you don't have a double bond, it's not going to be a cis-trans isomer. It'll be a different kind of isomer. Okay. Would we like to learn about another kind of isomer? Okay. If you need paper, there's paper at the back. Now, you are not responsible for knowing what the prefix but means, but does anybody happen to remember? But means 4, okay? So we have 4 carbons. But means 4, so we have 4 carbons. 1, 2, 3, 4. And we can number our carbons. Again, that you're not responsible for this. 1, 2, 3, 4. Where do you think the chlorine is attached in 1-chlorobutane? It's attached to carbon number 1, 4, yes. So there's our chlorine. What's on all the rest of the carbons? Hydrogens. And in fact, you'll often see it just drawn like that because we get tired and we don't want to draw all the H's. Okay, but I'm going to draw them on here just for the sake of, you know, being complete right this second, okay? What if I had 2 chlorobutane? Where would I put my chlorine? Where would I put the chlorine in 2 chlorobutane? I would put it on the second one. Okay. Now, could it be on the bottom? Now let's just take a look at this structure here. Is this structure, are these 2 structures isomers of each other? Can it spin? Those are single bonds. So it can spin. So therefore they are not isomers. Yeah, we could just spin that one like this, and then the chlorine's on the opposite side. Okay. Now, what if we had this one? Are those isomers? And you might think so because this is a flat structure. But it's not really flat. What you really have is you really have a hydrogen, hydrogen, hydrogen sticking off like a little tripod off the end. So does it matter whether the hydrogen is on which one? No, because they can spin. Okay. And if you're wondering what that looks like this right here. You see where we got 1, 2, 3, and this can spin, right? So this is what we're looking at here. Okay. So those ones are not isomers. Yeah, they also spin. Everything is like, you can rotate around any of the axes. Okay, yes? Not if it's a single bond, it's not an isomer. It's not an isomer if it's attached to the same carbon. Okay, so if you look, these 2 guys here are not isomers because if this carbon is doing the spinning, then it can go like this, or it can go like this, or it can go like that. Okay, so if it's on the same carbon, it's not an isomer. But if it's on a different carbon, it is an isomer. See how we've got the different carbon here? We've got carbon in the middle as opposed to on the end. So that is an isomer because the chlorine is in a different position. You cannot spin this one. You can't spin this one and end up with that. Does that make sense? Yeah? Okay. Now, here is one more question. Okay. We have C, 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 C. What if we had a Cl here? Are these 2 isomers? You can just flip it around. In this case, you're like, okay, my Cl is over here. If I take the entire molecule and go like this, now my Cl is on the other end. Okay, and in fact, no matter which way you draw it, you would actually, and this is again not part of what you're learning, you would actually number your carbons 1, 2, 3, 4, because you number from the end with interesting stuff on it. Okay, you don't start numbering from the other end. So there's no such thing as 4-chlorobutane because it would just be 1-chlorobutane. Similarly, there's no such thing as 3-chlorobutane because it would be the same as 2-chlorobutane. Okay. As I said, none of this is really part of this unit or anything, but they do like to bring up isomers sometimes in the written response, just like not as asking about you to understand this or whatever, but like, here's some isomers. Now use this information you already know to do something with them. And if you've never heard of an isomer, that might throw you because you're like, oh my God, what's an isomer? Am I supposed to know this? Blah, right? You don't really need to know anything about them. You just need to know that they exist and it is a word. And it's okay if you see it and you don't know anything about them. Okay? Yes. Isomers are super important in organic chemistry. So if you're taking, depends on the university, some of them have organic first year, some of them have it second year. So like some of them have a little bit in first year, some of them don't do it at all until second year. So depends. Okay, so here we have some cis-trans isomers. Over here we have structural isomers. Like I said, not too something to worry about. But now we're going to look at the strength of a sigma bond compared to the strength of a pi bond. Let's look at where our electrons are and where our nuclei are. My nucleus is here and here. These are where my positive charges are. And my negative charges are in the middle. Yes? Now with my pi bond, my nuclei are here and here. And my electrons are either up above or down below or some combination thereof. Which one do you think is stronger, the sigma bond or the pi bond, and why? Tell your partner. All right, my friends, over here. These electrons over here, are they further from or closer to the nucleus? They are closer to the nuclei because they're right in between them, yes? Whereas these guys here, they're sort of like up. They are between, but they're also like, they're not right here. They're like, oh, further away. So they are further from the nucleus. And the further we get, what happens to our Coulombic attraction? As charges get farther apart, absolutely, it gets Smaller. And if it gets smaller, what's going to happen to the strength of the bond? It's going to be weaker. So which one is stronger, sigma bonds or pi bonds? Sigma bonds are stronger than pi bonds. I'll tell you why people sometimes get confused with this. Because double bonds are stronger than single bonds. Why is that? They're made of a sigma and a pi, so you've got the stronger one and you've got another one that's like it's weaker, but it's both of them, so it has to be stronger when you have the combination. Well, not this test because this is unit 11 and we're doing unit 10 for your test. It could be, for sure. Yes? Yeah. Uh-huh. If they're spinning the same way, they can't be in the same orbital spinning the same way. What was the question? Oh, you mean if this one was this way? When they come together, one would start spinning the other way. Okay, they cannot exist in the same orbital with same spins. They have to be opposite spins. Physics says so. Okay, math says so. All right. Sigma bonds involve the overlap of sp and hybrid orbitals, which you don't know about yet. Pi bonds involve the overlap of p and d orbitals. And is that it? Here's our cis trans isomers. I think this is just talking about it. And this is just counting sigma and pi bonds. Would you like to try one of these together? Let's try this one. Okay, so cover up the answer. So we would go sigma bond 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then we have 15 and 16 sigma bonds, yes? All right, how many pi bonds do we have? One here for the first one, second one of our double bond, and 2 and 3 pi bonds. So yes, you should be able to count the number of sigma and pi bonds in a molecule. I don't know that it's a huge, great skill or anything, but you often get asked to do it, so there we are, okay? All right. Are we ready to move on to valence bond theory and hybridization? Huh? No is not an option. Now, I think, Janet, it might have been you who used the term table setting. Yes? Yes? This here, 11.1D is table setting. In 11.1E, which I have not yet produced for you yet, I'm going to give you like a so simple way of doing this that you'll be like, my God, why didn't you start with that? But at the same time, no one seems able to learn it that way. Like Ms. Wu and I were like, so what if I was to tell you, that if there are 4 things attached, 4 areas of electrons attached to a central atom, that the hybridization is sp3, 1, 2, 3, 4. Okay? And what if I told you if there are 3 areas of electrons around an atom, the hybridization is sp2, 1, 2, 3 things. Would it make sense? Yeah. And yet, No one seems to believe me, except for you. Thank you. Okay? People are like, I don't understand. Why is it sp3? It's like, because there are four things. S, PPP. S, PP. sp2. Three things. But we're going to go through this whole thing anyway, because probably you will run across it in university and you'll be like, okay, I learned this weird, stupid little trick to do it, and I didn't understand any of it. But bear in mind, if you don't understand any of this, it's probably okay. All right? This is a theory. It has been supplanted by other theories which are better, but it is easier to understand than molecular orbital theory. So I'm not going to be teaching you molecular orbital theory because it is not required by the AP curriculum, and it is quite, I remember it made my brain really, really hurt first year. It was probably one of the things that made my brain hurt the most. Okay, so we're gonna leave that for your university professors to deal with because we have enough. Yes? Supplanted means put in place of, okay? Did you have a question? Yeah, no? Okay. So we have valence bond theory and hybridization. Hybridization. So we have just been learning that in order to form a bond, orbitals must do what? Overlap, okay? So we think of covalent bonds as sharing these electrons because they overlap, and the resulting overlap region is no longer called an atomic orbital, it is now called a molecular orbital. Now, this would make you think we were learning about molecular orbital theory, but not really, okay? We're not there. And trust me, you don't want to, because then you'd have to learn about bonding orbitals and anti-bonding orbitals and that. Okay. What kind of orbital is represented in each of the unbonded H atoms to the right? To the left. What kind of orbitals are these? They're s orbitals. Are they 1s, 2s, 2p? What are they? They are 1s orbitals. What kind of bond is formed when those orbitals overlap? Sigma. Okay, so this is a 1s, this is a 1s, and this is a sigma. Here we have hydrogen and we have chlorine. What are our atomic orbitals that are represented here? In hydrogen, it is 1s. How about chlorine? It is 3p. Okay, so here we have a 1s and a 3p. What kind of bond have we formed here? It's a sigma bond. Here we have chlorine, again, but it's with chlorine. So this was 3p, so this one also has to be 3p. What kind of bond have we formed here? That is a sigma bond because it's the head-on overlap. What is the difference between the 3p orbitals in the 2p sublevel? What's the difference between this one, and this one? They're aligned differently. They are oriented in different directions in space. So the difference is the orientation in space. So other than that, they're the same energy, they're the same shape, they're just oriented differently. So here is hydrogen. Here is fluorine. Hydrogen, we have a 1s orbital, and it's going to overlap with fluorine's 2p orbital to form a sigma bond. Why does fluorine use its 2p orbital to bond with hydrogen rather than its 2s orbital? Chat with your partner, see what you think. Okay, why does fluorine use its 2p orbital rather than its 2s orbital? 2s orbital is full. I left a lot of space for that. I did not need that much space for that, but that's okay. Which two atomic orbitals would you expect to overlap in the following molecules? Bromine. So if you have a bromine and a bromine, which atomic orbitals would you expect to overlap? 4p. 4p. What about water? 1s. 2p. We're good with that? Because that's where we've got empty slots. Yes? Methane. Hydrogen would be 1s carbon, 2p, okay. And dihydrogen sulfide, 1s, and 3p. That's what we would expect. Oh, did you see how I italicized that? I'm going to underline it and put little stars because that is what we would expect. But if that was what it was, then there wouldn't be much more. And this is a very long document for not having anything more to learn about it. There's two problems with that simple overlap model. Let's observe our first problem. Here is carbon, ground state carbon. Now, how many bonds does carbon form? 4. How many unpaired electrons does carbon have? 2. Oh, that's kind of ugly, right? So this is problem number 1 if we just say, oh, we've got some p orbitals. Even if I was to so that's problem number 1. Okay? Based on this approach, how many bonds should ground state carbon be able to make? Only 2. And maybe a third one if you had someone willing to come in and shove a couple of electrons into that final p orbital. That does happen from time to time, but we're going to say 2 for now. How many CH bonds does methane contain? 4. So we really need to have 4 unpaired electrons, yes? Okay. So what we're going to do, and this is our first solution, is what we're going to do is we're going to call it, it's called promotion. When we have promotion, what does promotion mean? It means you are lifted up. So what if I took my original carbon here? We're just doing this in our head, okay? So this is not really like what happens in real life, okay? In real life, everything just kind of happens all at once. But this is what we do in our head to kind of make it make sense to our poor little human brains, okay? What if I took this electron here and I was like, nope, you go right on up there. You get promoted, okay? And so where is it now? It is here. Now, guess what? How many unpaired electrons do I have? 4 unpaired electrons. Isn't that good? Is that how many bonds we want? Excellent. Now you would think, oh, thank goodness we have solved our problem. Okay. So from which orbital was the electron and carbon promoted? From the 2s into the 2p. How many singly occupied? Oh my gosh, we've already done this, but that's okay. It has 4 singly occupied orbitals. If covalence bonds formed by the singly occupied orbitals, how many bonds can it form? It can form 4 bonds. For the CH bonds in methane to form, carbon's atomic orbitals must overlap with hydrogen's orbitals. What type of overlap would you expect to find in methane based on the configuration? You would expect carbons, we have a carbon has an S orbital, it has a p x orbital, it has a p y orbital, and it has a p z orbital. In fact, I should write it like carbon over here. It's what carbon has, yes? What does each hydrogen have? It has an s orbital, so an s, an s, an s, an s. So I would expect an s to overlap with an s to overlap with a p. Didn't draw that very well, p. There we go. My s to overlap with my p. And the s to overlap, God, I cannot, yeah, I know, to overlap with the p. Yes? They're the saddest little things ever, right? Now, we're going to consider the molecule H2S because it is a wee bit more simple, okay? A little bit simpler. The orbital for the diagram of hydrogen looks like this. Sulfur looks like this. 1, 2, 1, 2, unpaired, unpaired. So it looks like this one will work out okay. Yes, if I have H2S, I can have an S overlap with a P, and I can have a different S overlap with a different P. Everything is well and good. Now remind me, what are the orientations of the P orbitals? We have X, Y, Z. I don't even know which one goes in which direction. They are perpendicular to one another, okay? So if this was what would happen, we would have a hydrogen come in and overlap on one of them, and it would overlap on another one. And what's the angle between those? What's the angle between the p orbitals? That's a 90 degrees. And it doesn't matter which two we slot it into, that is 90 degrees. So we would expect H2S, if we were to observe that molecule, we would expect it to be an oxygen with hydrogens coming out at 90 degrees. But that is not, I am sad to say, what is observed, which is why this is problem number 2. So what is the bond angle predicted above? It was 90 degrees. Could you draw a Lewis structure of H2S? Why don't you do that over here while I charge my pen? Oh, there's my other pen. Yay. Okay, so this is H2S. Now we haven't learned this number yet, I think because I used to teach this at the end of the unit. So you're gonna be like, what is a steric number? Ah! A steric number is the number of areas of electron density, okay? Okay. So how many areas of electron density are there? There are electrons on the right-hand side. There's electrons on the bottom. There's electrons on the left. There's electrons on the top. How many areas of electron density are there? 4, and that's what we call the steric number. And don't worry if you don't know that name yet, we will get to it later. That's just what, I don't know why we call it the steric number. It does have to do with, there are stereoisomers, and I imagine it has something to do with that, but I don't know that for sure. Now, the actual shape of H2S, if I have 4 things, do you remember what shape we make? If I've got 4 things like methane, makes the little tripod, the tetrahedron, yes? So we really should end up with a tetrahedron. Tetrahedral. And the bond angle of a tetrahedron is 109.5. So in fact, if we were to look at a real H2S molecule, the bond angle is not 90 degrees, the bond angle is 109.5 degrees. So what we would have is we would have sulfur, we would have a lone pair coming out the top, and we show a lone pair sort of in its own little balloon, okay? We would have our little tripod coming out the bottom. We would have 1 lone pair coming out here, and then we would have an H coming out here, going towards us. We show it going towards us by drawing a blackened triangle with the bold end coming towards us. And then we would have another hydrogen sort of going back away from us. Okay, so that's our 3. There's a hydrogen and a lone pair and a lone pair. Okay? And the bond angle here is 109.5 degrees, not 90 degrees. So doesn't that suck though, because how are we supposed to overlap then? All the p orbitals are at 90 degrees. If we were overlapping with p orbitals, that bond angle would be 90 degrees. Yes? And it's not. So there must be more to the story. Okay? So here's our solution. And our solution is hybridization. Now, if you don't know what the word hybridization means, it means mixing two things together. Do you remember like that from genetics? So this would be like not, what do they call it? When you have, in genetics, when you have red and white flowers and you get pink, what's that called? Incomplete dominance? I think maybe. Because there's co-dominance where you would have like pink and white stripes, or sorry, red and white stripes. But then there's like, I think it's incomplete dominance, but I could be wrong because it's been about 20 years since I've taught genetics. At any rate, you get a combo of the two. So if we take a llama and we hybridize it with an anaconda, we get a llamaconda, which is a combo of the llama and the anaconda. Yes? I have to tell you, I don't know why I was so thrilled to get this little image here, but I was. So even if it doesn't make any sense to you whatsoever, you have to appreciate the fact that I went out and I found a llamaconda for you. Yes, because Lord knows I did not draw that myself. Okay, now, for real this time, we are not hybridizing llamas and anacondas. We are hybridizing S and P orbitals. Okay, so this is for sulfur. Now, if you recall, sulfur had like this, yes, 1, 2, 3, 4, 5, 6. And what we're going to do instead is we're going to mix these two together, the lower energy one with the higher energy. And we'll end up with 4 orbitals that are of a medium energy in between the two. Okay? So we've got some S-like properties, we've got some P-like properties, and we end up with sort of mess in between. And we have 4, instead of having 1 that's lower energy and 3 that are higher energy, they are all 4 of them degenerate. What does degenerate mean? They are all the same energy. And this is where you remember I was talking about sp3 at the beginning. We mix together 1 s orbital plus 3 p orbitals. Yes? And how we write that, and this is where it does get a little confusing because it no longer means the number of electrons, that little number at the top. This sp3, that means there are 3 p orbitals in the hybrid set. And there's nothing up here for the S because that would be S1. Okay, but we don't write the 1 because there's one S orbital. Now, if all these orbitals are degenerate, oh, look, I asked that already. It means they are all the same energy. Why are they named sp3? We have one s orbital mixed with 3. And the reason I'm writing it out as a number 3 is I don't want you to get mixed up between the quantity 3p orbitals with a 3p orbital, which is in energy level 3. Do you know what I mean? So that's why I'm writing it out as a word. 3p orbitals. So here is our 3 here, and our 1 is where we don't have anything written. And so if we have the electrons in unhybridized sulfur, it looks like these ones here, 1, 2, 3, 4, 5, 6. But now we have 1, 2, 3, 4, 5, 6. Weird, right? Just as weird as a Lamaconda. Yeah. So what do these new hybrid orbitals look like? Well, if we take an S and the 3p orbitals, what we end up with is orbitals that have one big lobe, sort of that big lobe is more S-ish than the P's. But then there's a second lobe, which is more P-ish than the S. And the 4 of them point in 4 different directions. They all point to the different corners of a tetrahedron. And in fact, you know what? If you get balloons, you will get the shapes. Like if you get 4 balloons together and you tape them together, they will not form like a little daisy. They will form a tetrahedron. Okay? So they point to the corners of the tetrahedron. Now, if we show them all together, all overlapping, because of course the nucleus is actually in the same position for all of them. They're not all separate like that. They are all in one place. Here is our nucleus. And we're only showing the large lobes because if you start drawing in the small lobes, it starts to get really messy. Okay. You can see there is a little balloon pointing to each corner of the tetrahedron. And our bond angle here, our angle between these orbitals is 109.5. So when we have the S with the 2 H's, we have that tetrahedral shape, which gives us a 109.5. Only works if we have the hydrogen overlapping with an sp3 hybrid orbital rather than a p unhybridized orbital. Phew. Yeah? Okay. So 2 of sulfur's sp3 orbitals overlap with the hydrogen's 1s orbital to form bonds. So this is an sp3, this is an sp3, and this is hydrogen's s and hydrogen's s.
Today's puzzle has been updated.
I thought they said that already.
It's crypto lockbox participants. Today's puzzle has been updated. Thank you.
Okay, now, what kind of bond is formed by this overlap? The S overlapping with the sp3. Is that a sigma or a pi? Is that head on or is that, this is sigma, yes? So we have a sigma bond here and we have a sigma bond here. What are the other two sp3 orbitals doing? They're chilling. What are they containing? They are containing lone pairs. You can go home and start working on the reviews if you want to, okay? Just work through workbook 10, whatever you haven't done. Hello.
Our question for question 7.
Yes.
So CO2 has resonance structures, right? Because it forms 3 bonds on one side.
You could, but it's much less favorable.
So this question is asking like,
I would say these 3 definitely do, and that one doesn't.
like
If I had to.
This doesn't have resonance structures.
Yeah, it's not an awesome question. I wouldn't put that on the test.
Because they're unoptimal, like in terms of formal charge.
The formal charge is ugly. Yeah.
So
a better question for this would be, which of the following species are best described using resonance structures if all the resonance structures give the most favorable formal charges?
Okay.
Okay, but I wouldn't give you this question on a test because obviously it's not a good question if it requires that many words to make it a good question. Yes?
Does it count as resonance structures if they have bad formal charges?
Kind of, but not really. I don't know.
Okay.
That's my best answer is I don't know. Hi.
Wait, why is it 109?
Why is it 109.5? So if you were to take 4 balloons and tape them in the middle, they will arrange themselves as far from one another as possible.
But then if you think of like the p orbitals, it's like 6 of them, right?
Yep.
So then why would it be like 4?
Why would what be 4?
Like you're saying like 4 balloons, right? Like I can have 4 balloons with arrange themselves like that.
Because there's one s orbital, and there's not 6 p orbitals, there's 3 p orbitals.
And then the 3 p orbitals would be like
P, and S.
Wouldn't the p orbital? So wait, if it's like, let's say it has like 3 ends, then would it be the
3 what?
Like instead of 4, it'd be like 3, right? And then would it be different?
So if you mix up one s and with 2 p orbitals, you end up with an sp2 hybrid, which has 3 lobes.
Lobes?
Yeah. So if you left one p orbital unhybridized, we'll get to that next day. How about you just not worry about it? Worry about chapter 10 for now. We'll talk more next day if you still have the question asked then. Hi.
3, 5, and 7 is it just because it's sulfur? Like
Yes, because it's in the 3rd row or below. Only if it's in the 3rd row. So this one has C and beryllium, which can't. This one has carbon, which can't. But sulfur and phosphorus are in row 3 or below. Yeah.
And, so the formal charge, how do you do that again?
You take the valence electrons for that atom, and then you subtract the assigned electrons, and for the assigned electrons you count each dot as 1, and you count each line as 1, because it gets like half of the electrons from a bond. The other atom that it's attached to gets the other half.
Wouldn't it just have 8 every time then? Or how does that work?
So here, for chlorate, Yeah, and that's because so chlorine has 1, 2, 3, 4, 5. Okay. So
7 minus 5.
now actually this is a deep question because chlorine is in row 3 or below. So in theory, we could give it another bond.
Because it can expand it, right?
Yeah, it can expand its octet. So if we did that, because here we would have 7 valence electrons minus 5 assigned electrons would give us a charge of +2. That's not a very happy formal charge, right? Yeah. It's quite big. But if we do this, because it's in row 3 or below and it can have an expanded octet, then we have its formal charge will be, there's 7 valence electrons, and now we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 assigned electrons. So that gives us a +1, but I think we could do even better.
Can we do it to each side?
We could do it to the other side. Yes, we could. So let's do that instead. Let's move that one there. And now we have 7 assigned electrons, and now we have 0. We've also made oxygen better because oxygen has 1, 2, 3, 4, 5, 6, which goes with 6 valence electrons. 1, 2, 3, 4, 5, 6. So the only one that now has a formal charge is this guy, which has 7 assigned electrons, so it's -1. Okay, so and there's no need to do it to this one here because then you would be starting to make this negative and that one positive, and then that's not a happy thing either. So just once you get to this point, you can leave it. You could have a resonance structure where it was here, or yeah.
Are we expected to do it like this or just like that?
I think probably like this. I don't think it's likely to come up, but I say that about everything, right? So the formal charge on the Cl atom here would be 0 in the most favorable structure.
I did 0, but then it was like, I think it was 2 and like.
Oh, okay.
2 here.
Yeah, I feel like that's because it was based on this structure. So it's not a good question, is it? That's what you get when you throw things together, you know, the morning of.
That's like a multiple choice.
Yeah, yeah.